Is data science an extension of John Tukey's exploratory data analysis? Data exploration and pattern recognition through data visualization are widely recognized as essential features of modern data science. In the 1960s and 1970s, prominent statistician John Tukey introduced exploratory data analysis, EDA, as a revolutionary approach to overcome the rigid and often questionable reliance on hypothesis testing, or confirmatory data analysis, CDA. However, Tukey's vision remained on the fringes of the statistical mainstream. Academic journals favored the neat answers provided by hypothesis testing, and EDA was largely omitted from statistics textbooks, often reduced to a passing mention. With the rise of data science, however, the tide has shifted. Many of Tukey's once overlooked ideas now form the foundation of data science practice. In industry, EDA is regarded as an indispensable component of business intelligence. In this sense, data science can be seen as the modern extension of EDA, made possible by new technological conditions and the explosion of data availability. Exploratory data analysis is not a fixed set of methods, but rather a philosophy of data analysis, an attitude of curiosity and flexibility. Tukey often compared the EDA process to detective work, where the analyst explores data from multiple angles to uncover a plausible story without imposing preconceived hypotheses. Importantly, EDA is not a fishing expedition or an exercise in forcing the data to yield an answer, such as p-hacking. Instead, it focuses on uncovering insights that are already present in the data, de-emphasizing rigid mathematical assumptions and theoretical probability distributions in favor of real-world observations. Tukey's approach encouraged researchers to embrace complexity and uncertainty, prioritizing exploration over binary conclusions like reject or fail to reject a hypothesis. This philosophy of open-ended discovery is at the heart of what makes EDA both timeless and forward-looking. At its core, data science shares key principles with EDA. First, like EDA, data science does not begin with strict preconceptions, narrow questions, or tightly defined hypotheses. Instead, it aims to uncover hidden patterns inherent in the data itself. Second, both disciplines rely heavily on data visualization to explore and communicate insights. Data science techniques such as classification trees, neural networks, and k-means clustering are data-driven methods that align closely with EDA's exploratory spirit. Finally, both EDA and data science emphasize model verification through techniques such as resampling, including bootstrapping and cross-validation, which ensure that findings are robust and reliable. Despite these commonalities, data science represents a significant evolution from Tukey's EDA, largely due to technological advancements and new challenges posed by modern data. Computational power and data size. When EDA emerged in the 1970s, computational resources were limited, and datasets were small and structured. Tukey's classical tools, like stem and leaf plots and box plots, were designed for manual or paper and pencil implementation. In contrast, data science thrives in an era of high-performance computing, where massive, complex datasets, big data, are analyzed efficiently. 2. Dynamic visualization. While EDA before the 1990s relied on static visualizations, modern data science leverages interactive and dynamic statistical graphing tools, enabling analysts to explore data in real time and from multiple perspectives. The visualization revolution has brought Tukey's philosophy to life in ways that were previously unimaginable. 3. Unstructured and semi-structured data. Traditional EDA focused exclusively on structured numeric data. Today, data science extends its reach to semi-structured and unstructured data, including text, audio, and video. This expansion has dramatically broadened the scope of exploratory analysis. 4. Automation and machine learning. Machine learning, a defining feature of data science, allows computers to automate model building and optimization. While EDA relied heavily on human judgment to verify models, machine learning can fine-tune models automatically. However, this automation introduces challenges of transparency and interpretability. Methods like neural networks often function as black boxes, a stark departure from Tukey's emphasis on human-guided exploration and interpretability. For decades, EDA remained an underappreciated, marginalized approach in statistics. Few could have foreseen that Tukey's once radical philosophy would experience such a resurgence. Yet the emergence of data science has transformed the analytical landscape. The explosion of big data, advances in computing power, and the growing importance of visualization have finally allowed the principles of EDA to be actualized on an unprecedented scale. The story of EDA's revival holds an important lesson. Innovative ideas may lie dormant when the conditions for their success are not yet ripe. Tukey's exploratory mindset, once overshadowed by the rigidity of hypothesis testing, has found new life in the dynamic, technology-driven field of data science. Far from being a relic of the past, EDA serves as a reminder that the most powerful discoveries often begin with open-minded exploration and a willingness to embrace uncertainty. In this light, data science is not just an extension of EDA. It is a fulfillment of Tukey's vision. As technology continues to evolve, the principles of EDA will remain central to the quest for understanding, reminding us that exploration, curiosity, and creativity are the true engines of scientific progress. The moral of the story is clear. It's never wise to judge prematurely who will have the last laugh. The seeds of exploration planted today may blossom in ways we cannot yet imagine. Thank you for watching and happy exploring.